All right. Sam, sorry, we forgot to record this, so just starting right now. All right, so let's look at if I have a graph like this, we consider that to be concave up. Concave up. Curved in such a way that it would hold water, if you will. All right? And then the reverse of that, of course, would be concave down. Now, we don't want to confuse that with convex, or I don't even know the difference. I don't even know what that means. But, so concave up and concave down. All right? And you get curves that have some of both in them. For example, if you take a look at x cubed, right? There's a place there, and we talked about this with that balloon graph. There's a place in there where it switches. You know, we talked about the balloon where he was going up faster and faster, and then all of a sudden started leveling off. So it was going up faster, faster, and then it started leveling. There was a place kind of right in the middle there where it seemed to switch. And that's called the inflection point. The inflection point right there. So this would be concave. What is it before the inflection point here? Concave what? This is concave down and then switches to concave up. All right, so you get a graph that's got both parts of it. It's concave down for a while, switches to concave up. It's increasing the whole time, so don't confuse concave up, concave down with increasing, decreasing. Those are different. You can have a graph that's, well, right over here. We've got this, the right half of this is increasing and concave up, but the left half is decreasing and concave up. When we talk about increasing, decreasing, we're always talking about from left to right. Okay? This graph is increasing and concave down until here, then it's decreasing and concave down. It's concave down the whole time, but it's increasing the first half and decreasing the second. This graph is increasing the whole time. Concave down first and then concave up. All right, so those are some terms that are important. All right, if you look at page 15, it talks about if you had a table of data and we're asked to graph it, you really don't know. I mean, really, this bottom left one's really the only graph that would be correct for a table of data if that's all you had. You would only know those individual points. I mean, it could be any of these. It could be a bunch of line segments. It could be a broken thing with some curves and, you know, that kind of piecewise, or it could be just a nice smooth curve. I mean, it could be all those things. So when we have a table of values, we don't really know. Okay? All we can know for sure is that. Okay? All right. Next thing I want to do is look at a couple of these, the next couple pages. I want to look at those documents that I sent to you. So if you would go on your calculator, and I'll have somebody be presenter here. All right. Oops. What happened there? Everybody connected and logged in? Says they are. There we go. Who'd we get? Carrie. All right. Yay. All right. So go to My Documents. All right. And you go into the AP Calculus Period 3. And let's first grab the transformations translated. Let's get that one and open that one. Now, it's asked if you want to save. I would say no. I would say no. I'd hit cancel there. That's the document you were doing that you opened up when you did the scavenger hunt thing. Okay? So at least we know Carrie was doing the homework. So I would just say no. I don't think it's important to save that. Okay, so we open this one up. Transformations translated. All right, go ahead to the next page. Control right arrow will take you to the next page. Okay, and we've got a basic parabola there. Can you grab that point in the middle there? I just found these this morning or last night. I just downloaded them this morning onto my calculator to send to you, so I haven't had a chance to really play with it. So now one way to grab, notice in the middle here, if you hit Control and then click in the middle, it'll turn into that closed hand. Or if you just hold down the middle and hold it. I'm trying to drag that to the right. Oh, okay, so that drags the whole parabola. Okay, see what it's doing now? Okay, go ahead and drag it a little more. Okay, that's fine right there. Now, I thought it'd be interesting to send this to you, so if you wanted to investigate this a little more, if you're having trouble seeing it or whatever, you could go into this and you'd have it in your own hands and you can do it. But notice what happened when we grabbed that parabola and drug it to the right. Notice what it did to the graph. Do you guys remember this last year? I know you did it in advanced math with the shifting and moving and stuff. Okay, so hopefully this will be pretty easy. Okay? Because I encouraged the advanced math teachers a number of years ago to make sure and emphasize this. And so now notice we went to the right, but it says minus, right? I mean, so it's kind of the opposite of what you think it might be. Okay, drag that back to the 0, and then go left. And of course, we know what's going to happen, right? We're going to have we got an x plus, we got a plus in there, right? Okay, and now go back to the 0 again, and now go up 1. Okay, now look what it did, right? It put a +1 on the outside of the square. Now remember, those other ones were on the inside, okay? And then drag it down. Okay, and we got a -1. Okay, so now what we have there, I think what I would like to refer to those as, what I will typically refer to those as shifts. Now last year you used to talk about a phase shift, but that was only with the sine curve. Okay, so if I come back to here, so Sam can see it. All right, so here's what I would put in your notes about this. I would say, let's do the vertical shift first. A vertical shift is when you take f of x and add something or subtract something to the outside. So a vertical shift of k units. So if you go +1 or +2, that's going to move it up. And if you do -1 or -2, that's going to move it down. Okay? Now a horizontal shift, that was when it was on the inside of the function. Okay, so that's when, and it was opposite. So you have a minus in there. So if you're going to go to the right, it'd be -2, and it's on the inside of the function. Okay, so we have vertical shifts and we have horizontal shifts. All right, now if we go back to Carrie's document, okay, you go ahead and shift that back up to the 0. Now, it works with x squared, and you saw it work last year's time, but it works with a lot of other stuff. Go to the next document, or the next page, I mean. Okay, now, here we got the absolute value graph, right? They call it the a of x function, okay? So grab that k and drag that up. Drag that slider. Ooh, I don't know what you got there. Hit escape. I don't know what that is. There it is. Okay, now we're shifted up 1. Okay, and so again, notice it puts a +1 on the outside. And that's if it's the absolute value function. Okay, now click this little triangle up here, this little up triangle. And what that does is it changes it to a new function. Okay, and let's say we had this piecewise function called b of x, right? So now grab that k equals 1. Now let's look at this point they've got for us here, -2, -2. If she drags that up, she drags that k up 1 to 2. Notice how it's just taking the whole thing and it just shifts the whole thing. So it doesn't matter if it's a parabola or a v-graph or whatever it is, whatever function it is, if we add 2 to the outside, now that's important. It's important to understand that a vertical shift is when it's on the outside of the function. That makes sense. Output, outside, okay, it affects the outputs, the y values, the up and down. When you have it inside with the x, it affects the inputs. And the inputs go horizontally. So let's go to the next document, or the next page. Go to 1.4. Okay, and here's one. This happens to be the square root function. Okay, now notice we've already done a -1 on the inside. This is the t function, it's called. Okay, we've named this one the t function. This is actually square root. It's a top half of a sideways parabola. Okay, we'll talk about that more tomorrow. But it's already been shifted 1 to the right. Go ahead and grab that and shift it again. If you shift it 1 to the right, it just takes all that. Okay? See, so our goal, my hope, is that if we, not on this quiz this week, but in the not too distant future, if we've got a no calculator quiz, and I ask you questions about this graph right here, this function, that you would know what that graph looks like. That you would know, oh, that's a square root graph. The square root graph is the top half of a sideways parabola. And it's the square root graph shifted 3 to the right. And so right away, just by knowing that, you'll know domain and range, you'll be able to visualize it, you'll be able to do all kinds of stuff. Because on the no calculator part of the AP test, that comes in, that becomes really important. Okay? Click that little up triangle there. Oh, yeah, that's okay. That's okay. We've shifted it 6 to the left, which is no problem. Hit escape. Hit escape. Hit escape.
Okay.
Hit escape. Okay. It's it's still catching up with all the things you've been clicking. Okay, so now we're ready. Now click that up there. I should be able to click that up there. Okay, so here's a new graph that's been shifted 6 to the left. Okay, from what it was originally. And again, you see the x plus 6 on the inside. All right, so that's all we really need in this document. So let's go to the doc menu. Go to the doc menu. Go to File. We could have went Home too, but while we're here, we can go to number 2, Open Document. This is just another way to get to our next document. There we go. And that just brings this up. Let's grab that one that says Dilate. No, you don't need to save changes. That's fine. Okay, so that last one was called translations. I call those shifts. Okay, they're the same thing. This one's called dilating. I call this stretching or compressing. Stretching or compressing. Okay? So, wow. Is everybody taking this off? Yeah. Okay. All right. So go to the next page. All right. So I want you to watch, over on the left, it says y equals ax squared. So this is our basic x squared parabola, and we're going to multiply on the outside of it. So this is going to be a vertical, and I'm going to call it stretch / compress. Okay, it's going to be a vertical stretch or compress. So if you grab that point, grab that dot, and right now we're looking at y equals 1x squared. If you grab that dot and drag it up, okay, keep dragging a little bit. There we go. Stop right there. So what happened there is we took that, and it took all the dark red part of the graph now. All of those y values are twice as big as they were before, including down here at 0. What's twice 0? Still 0. So down here it didn't change, but all the y values are twice as tall as where they were before, because in the other graph it was down here at 1, now it's at 2. Okay? So the graph is y equals 2x squared. So that's called a vertical stretch. Now, grab that thing and drag it right down to about here, down to about 1/2. Okay? Right about there. Perfect. Okay? So they call it a shrink, vertical shrink. I call it a compression. Okay? So if that number is greater than 1, it's a stretch. And if that number is between 0 and 1, it's a compression, like if it's 1/2 or 1/3. Put this on the screen here. So if A is between 0 and 1, then we've got a compression. If A is greater than 1, then it stretches it by that factor. If it's 1/2, it compresses it by a factor of 2. Okay, compresses it by 1/2. All right, and that's on the outside of the function. So that's if you have A times f of x. All right, if we have A times, all right, if we have a number, and you guys remember that as amplitude. If you had like 3 sine x, right, that means it'd go up to 3 and down to -3. And that's important to understand that it's not only, let me go back to here. It's not only above, it not only stretches it this way, but it also stretches it down this way. Because if you take all the y values times 2, all the positive ones get twice as big, like 3 would become 6, and -3 would be -6. So it goes both ways. So right here, it stretches from right here. Okay, now, that's all I've got on the calculator screen, I think. Go to the next page. I'm not sure. Yeah, that just shows what it does to those values. Okay, go back to the last page. Okay, and now grab that point and drag it below the x-axis. Okay, now we've got a flip or a reflection. So a vertical flip is when the A is negative. Okay, if you have A times f of x. All right, if you have an A on the outside, now again, these are all vertical because they're on the outside of the function. Okay, so when it's on the outside of the function, if it's adding or subtracting, it's a vertical shift. If it's adding or if it's multiplying, then it's a compression or a stretch vertically, or it's a flip vertically. Okay, so what's left? What's left? Horizontal, stretch, or compress, or flip. So a horizontal stretch or compress, what do you suppose the difference is? Well, how do you suppose it's going to look? How do you suppose the function is going to look if it's going to do horizontal? That's right. You're going to have f of A times x. The A is going to be on the inside. And again, if it's a stretch, now, wait a minute. Remember what happened when we put the shift on the inside? It was the opposite of what it looks like it should be. A minus actually was right, and a plus is actually left. Well, guess what happens here? A stretch is actually, sorry for writing so small, a stretch is actually the opposite. If you put a 1/2 in there, it's going to stretch it horizontally. And if you put a bigger number in, like a 2, it's going to compress it. Now, and then if A is negative, you're going to have a horizontal flip. If you have a negative on the inside, you're going to have a horizontal flip. All right? Now, the simplest example I can remind you of from last year was this. Sine 2x. Does anybody remember what that 2, how that affected sine? I'll give you a hint. Sine has a normal period of 2 pi. So when you graph the sine graph, right, here's 2 pi right here, and here's pi. That's the normal sine graph. What's sine 2x look like? The period is you divide by this number. Remember that? You take the normal period and you divide by that number in there. So the period of this one is going to be pi, which means it would go up, come down, and come back in pi units instead of 2 pi units. Well, what is that? Is that a stretch or compressed? That clearly compressed it horizontally by a factor of 2. So a 2 on the outside is going to stretch it, but a 2 on the inside is going to compress it by a factor of 2. If you had a 1/2 on the inside, that's going to stretch it. Because 2 pi divided by 1/2 would be 4 pi, so your period would be 4 pi, so it would be stretched out. Okay? Now, we're going to talk about periodic functions here in a second, but that whole idea of changing the period stuff, it only applies to periodic functions, something that has a period that repeats, okay? But parabolas, any kind of graph, we can stretch or compress. All right. Now, let's take a look at just a few more things, and then we'll see if we can give you a little bit of work time here. But let's do it. All right. So that's all we need with those documents, and you can go back into those and mess around with them and whatever. But there's 2 or 3 more definitions we got to talk about. Okay, we just were mentioning periodic, so let's look at that. What's a periodic function look like? Okay, if you could say in one word, if somebody says to you a periodic function, what's the first word that comes to mind? Chemistry people. Yeah. What's the first thing that comes to mind? A function is periodic, like the sine graph. Why is it periodic? Repeats. Repeats. When it be repeats, I mean, to me, that's the word that would come to mind. It repeats. It repeats. You got to be careful. It's the fact that it repeats outputs, and it repeats them in a consistent way. Okay? For example, if I gave you this graph here, is that a periodic function? Would you think that's periodic? Now, if the only definition was it's something that repeats, you might say yes. This does not repeat outputs. Okay? It keeps growing. All right? The sine graph repeats its outputs, and it repeats its outputs every 2 pi. For example, this one right here won't get repeated again till right over here when it's on its way up, 2 pi. Every 2 pi, you will get the same output as what you got 2 pi before that. All right? Here's the formal definition of that. What that is saying to you is that even if you shift that graph to the left, you could put plus or minus in there actually. You could put any multiple of p, 2p, 3p. P is the period. What this is saying is that you could shift the graph left 1 period, left 2 periods, right 1 period, right 2 periods, whatever. Then their outputs would be equal. That's what the f of x plus p and the f of x is saying. It says you put an input of x, and you put in an input of x plus p, which is p units more or less. We could write plus or minus there. You get the same output. You always get the same output. Okay? That's typically what it is. So in the homework, they're going to ask you some questions about periodic and using that notation and see if you can kind of figure out what it is you're talking about. So it seems pretty simple. A periodic function repeats like sine. Okay, that's easy. But then actually put that to use in some function notation and thinking about functions can be a little more challenging. So work on the homework and see how you do. All right, the other 2 things we're going to do is even odd functions. Now I know you did this last year because I was just in the Honors Advanced Math class subbing the other day and we were doing even odd functions. Okay? So, been a while probably, but you've done it. Somebody give me an example of an even function. Hit the word even is important. Okay, cosine is, now that doesn't necessarily make me think of the word even, but cosine is an even function. What's another one? X squared. Those are both even functions. Let's draw quick graphs of those. Here's the cosine graph. Here's x squared. What is it about those 2 graphs that makes them even functions? Fold them. Fold them. They have what we call y-axis symmetry. we can fold them and they will fold right on top of each other. Right at the y-axis, we can fold them. Okay? Now, there is another thing I want you to remember about even functions that I think is important. The more formal definition, and this is what we want to think of because we're really working on this function notation, I want you to think of that right there. An even function means this, that if I put in an a or a negative a, I'll get the same output out. If you think about a parabola, if you go over a units, you go up. You go over negative a units, you go up the same amount. What I like to call that is opposites in, same out. Opposites in, same out. So you put in 2 and negative 2 and x squared, you get 4. You put in you put pi into cosine, you get negative 1. You put negative pi into cosine, you also get negative 1. Opposites in, you get the same out. Okay, that's an even function. Give me an odd function. Sine x. Give me another one. Well, if x squared is an even function, x cubed has got to be an odd function. Let's look at those two graphs real quick. Sine and x cubed. Right? Now, what kind of symmetry do those have? Be careful now. Origin symmetry. Everybody always wants to say x-axis symmetry just because the other one was y-axis. It must be. It's called origin symmetry. What it really means is if you put opposites in, you get opposites out. F of negative a is equal to negative f of a. Opposite outputs. Remember we said f of x or f of a is the output, right? F is the output, so negative f is the opposite of that. So this is opposites in, opposites out. Think of x cubed. You put in 2, you get 8. You put in negative 2, you get negative 8. Opposites in, 2 and negative 2, you get opposites out. 8, negative 8. Okay, that's an odd function. What kind of function would have x-axis symmetry? Wouldn't be a function. If you have a function that has x-axis symmetry, it means you could fold it on the x-axis. Well, it's not going to be a function because it's not going to pass a vertical line test. So no function has x-axis symmetry. This is called origin symmetry, y-axis. Okay, so you'll have some questions about even odd functions. But the idea is that if we know a function is even or odd, then we know something important about it, and that'll usually help us in problems. Calculus. It'll help our calculus if we know functions are even or odd or something like that. Okay? We can take some shortcuts. So those are important properties of functions. Okay, so for your homework, and I am going to try to help you get started. I'll give you one hint on one set of problems, but it's going to be the 1.2 homework questions, okay, on your assignment sheet. Okay? All right, so you can kind of get those out. And I want to help you with 35 and 40, or 35 through 40. All right. Okay, here's 35 through 40. Now, there's this graph, I don't know, it's called the what? G? F? Something? G. That's the G graph right there. Okay? Now, you've got 6 problems here on 35 through 40 where you're supposed to do some sort of shift or stretch or compress or something. So when I come around and look tomorrow on 35 through 40, I expect to see 6 different pictures. Okay, a new picture for each one. Now, what I would suggest, whenever you're doing, remember on that calculator thing that Carrie led us through, there was always one point that she was dragging and you could see it change. Now, all the points were changing, but you could see that one change. I think the easiest way to do this is to locate what I call the important points on this function, which would be the intercepts, missed one, and the corners, and those kind of things, the local max, mins, those kind of things, kind of those important values. Now, if they ask me to do g of x minus 2, what does that mean to do? Shift it down 2. So if I take every one of these points and move them down 2 and then connect them, boom, it's easy, right? So shifting's always easy anyway. Okay, so left, same thing. If I want to shift this left 1, I take all these points and shift them left 1. Right? And then there's my new graph. So shifting's pretty easy. All right, what if I have g of negative x? What is that? That's which way? It's on the inside, so it affects the inputs, and the inputs are horizontal. So it's going to be this way. So this point will go where? Instead of being here at negative 4, it'll be there at positive 4. And this point, which is over here at negative 5, will be over there at positive 5, right? And they'll just flip that way. And then you flip all those points. What about this point right here? It'll stay the same, right? Okay. And then let me give you one more. This is always kind of the trickiest one. What if I had g of 2x? A 2, we said, was a compression by a factor of 2. So that means this point right here wouldn't it go there? Because by compress, we mean come this way, right? Towards the y-axis. So if this, and it's horizontal because it's on the inside. So it's a horizontal compression. So this point's over here at negative 5 horizontally. It's now going to be at negative 2.5. Be halfway in. And this point, halfway in. And this point, come in halfway. 1. And this point, come in halfway, right? And this point, in halfway. And you bring all those in, and then you've got your graph. So this one would be in halfway. This one would be in halfway. This one's going to stay. This one would be in halfway. This one would be in halfway. This one would be in halfway. And now, sure enough, that thing looks like it is. Oops. That thing looks like it is. Right? And then the stretch, of course, will gaps away. And a vertical, something on the outside is going to make them go this way. Okay, both up and down. Okay, anyway. So that's to help you get going on that. So, rest of the whatever little time. We got 12 minutes. That's okay. Better than the other class. So you can get started on that if you want to. If you have any questions, let me know.
Do you have any graphing paper?
Yeah.